Welcome back everyone to the Hello World Guide. This is another episode of the Raycaster series, and in this video originally I planned to implement the pathfinding, but I decided we should do some optimizations first and then we'll get to the pathfinding. So if I go ahead and run my game right now, what you can see is that the performance is okay at this resolution, the default one of 960 by 540, but if I actually maximize this at a higher resolution, you can see that the performance drops quite significantly to around 30 frames per second, which is quite obviously very low compared to what we actually want this to be. So I'm going to go ahead and close this and exit, and what I'm going to do is I'm going to go ahead and we're going to see where we actually need to optimize this. So first of all, I'm going to open up main.cpp, and so that we can get a bit of a better idea of our frame time, I'm going to disable vertical sync temporarily. So you can see now, you can see at the default resolution it's running at around 100 frames, while at maximal resolution it's running again at 30 frames. So I'm going to go ahead and open up renderer, and it's quite obvious that our renderer is our main bottleneck. So if I go ahead and open that up, if you were to do some profiling, you'll quickly find that the main place that we are spending most of our time is the actual floor rendering. So if I just, for example, just to show you, if I remove all of that, you can see that the performance is quite higher. So it's like 500 frames per second by default, and around 80 frames per second when we are at maximum level. So this is actually means that this is where we need our optimization. Now the point is that this place doesn't actually have like a lot of things that we can optimize. Like we've got some stuff here, but there's not really much we could optimize. We could do some stuff to make it faster, but what we really need is to actually run this in parallel. So currently you can see that we are going over all of our all of the our values from like top to bottom for our screen, each row of the screen, and then we are actually going each row of half of the screen, the bottom half, and then we are drawing the floor and ceiling for that. So if we want to optimize this, what we can do is we can not just do this sequentially, but do some of it in parallel, since this does not depend on the other ones. And in order to parallelize this, we can use the C++ std async function, which is quite nice for parallelizing this sort of thing. So what we're going to do is we are going to use that to kind of parallelize this, and in order to do that, what I'm going to do is I'm going to go here and I'm going to create a lambda function, and I'm going to just create a small lambda here, which is going to be called we can just call it draw row, we can call it that. And we're going to have it be just a simple lambda here, and we're going to go ahead and take all of the code of one iteration. So we're going to take all of this and we're going to take it and we're going to put it here, and of course we want access to all of our stuff in here, so we're going to just put and here to capture everything, and then this y value we are actually going to take that as an argument in our function. And the other thing quite obviously is our screen pixel, so we're going to actually define this first before we have that, so we're going to have to define it up here. So you can see that this is our screen pixels and this is the lambda that we'll use for drawing. Now what I will do is I will go here and I will create another lambda which I'll call a row loop, like that, and this is going to take two arguments. One is going to be a start value and one is going to be an end value. This is basically going to be a wrapper around having a loop that goes over a specific section of the screen and draws the rows there. So we are going to basically have a smallish for loop here, which will go start from our start value and go till the end value, and it will just call our draw row lambda or function, whatever, and we're going to call that with this value. So to run this asynchronously, we will use the std async function. The std async function basically tries to run this in parallel, but well, it doesn't actually guarantee that it will be run in parallel. What we can do is we can specify a launch policy to force it to run in parallel, but we're going to just let the computer decide whether to run in parallel asynchronously with the other stuff or defer it. But the idea is that we pass it a function, for example our row loop function, and we pass it a value from which it should start and a value at which it should end. And what it will do is it will return a value of type future which we can store. For example, we can say task is equal to this. And the way this will work is that we can this will basically now be running asynchronously. It of course depends, it might not run asynchronously since we are not specifying a launch policy, but most likely it will be running asynchronously. And what we can do is we can go ahead and wait on this task when we need its result. So you can see we are having our screen buffer and we are drawing it here. We are going to take all of that code and we are going to put it in the very end when we are done drawing everything. And since we do want to draw our walls after drawing this, we are going to take our wall drawing and we are going to put that at the end too, so that we have got all of our drawing in one place. And before we have got our screen drawing, the main floor and stuff, we want to actually wait on this task. What that will do is it will basically wait until this task completes. And of course, before we actually use the results of this, we do want it to complete. So we want to wait on it for here, and all of this while between when we are starting our wait and ending, it will actually be running like asynchronously, and this is going to improve our performance. Of course, currently we are running only one task, so it's actually not much difference and it's not much likely to lead to a performance gain. You can see it actually leads to still the same performance. But what we can do is instead of having one task, we can have multiple tasks. So we can create an std vector of futures. So we can use future here, and we just need to specify the return type, which is void for our function, and we are going to create a bunch of these, and we are going to call this tasks. And then we are going to create a const expression size t, which we are going to actually we can make this an array. So let me create a const expression size t here, which I'll just call number of tasks, and we are going to specify that as 8 for now, and 8 is going to work quite well. I think it of course depends on how many cores your CPU has, kind of, but not really. It's going to be a not specified launch policy, so it should automatically defer it or create a new thread depending on what the compiler sees to be the most suitable thing. Of course, we can specify an execute policy if we want to, but we are not going to do that. So we are going to use an array here instead of futures, and we are going to specify the number of tasks here. And what we will do is we will basically go ahead and loop over this. So we are going to say for I is equal to 0, I is less than num tasks, I plus plus, and here we are going to have to create a new task for this. So we are going to remove the single task that we have got here, and in the end we will actually go over each of our task inside of our task list. So we are going to go for each of the tasks inside of our tasks here, and we are going to wait on each of those tasks, actually 4 here. Alright, so we are going to go up here, and where we are actually creating our task, what we will do is that we are going to go up here, and now you can see we are looping over our task, and the idea is that we essentially need to set this and create a new task for each one with the appropriate values for the start and end. So for the start, the way we will calculate that is we will go ahead and say our start is equal to height by 2 is our base start plus our I multiplied by a value that represents the actual how many wall rows we should render in each task. So the way we will calculate that is that we can just say actually size t, we'll just use size t here. We are gonna say we can call this our num rows and per task, and we are going to go ahead and calculate this by taking the total number of rows that we need to draw, which is height by 2, convert that to a float, and we are going to divide that by the total number of tasks that we have got, and then we are going to use std seal on this to get round it up always, so that it never like misses a task or anything, or else we will have a blank strip of screen up there that is not filled. And then we are going to take our I and multiply that by the number of rows per task. So this will go up, and then we are going to go ahead and do similar for end, but for the end we are going to basically specify our number of rows per task, start plus number of rows per task, but we are going to actually do a bit of a conditional operator here. So if our I is equal to number of tasks minus 1, what that means is that we are at the last task, then we are going to just specify our height, because then we don't want to draw any additional ones that we have, because we are using std seal here. We might actually have some additional value here calculated, because we are rounding up, and if it is, then we don't want a segmentation fault, because it will be accessing values outside of the screen. So if it's the last one, we are going to just end at the height, and then we are going to create a new task. So we are going to go ahead and say our tasks, and we are going to say I is equal to std async, and we are going to call that, and we are going to provide it with our row loop function, and we are going to specify our start and end like this. And now if I go ahead and run this, what you can see is that it should be much faster now, and you can see that by default it runs at like 200 or 100 frames per second. And if I go ahead and like maximize this, you can see it's more to 40-50 frames per second. But mainly that's because I am recording as well, and if I actually don't record and I just run this standalone, then it is more to the order of like 70 or 80 frames per second, which is quite good at this resolution. Standard Raycaster running at 80 fps is kind of okay, considering that we have got textured floors and we have got our textured stuff as well. Of course there are things that you could do to optimize this further, but we are going to pretty much be content with that, and we are not going to do anything else. So anyways guys, this is going to be pretty much it for this video. I'll see you in the next one. Make sure to like and subscribe as well, and share this video with other people as well, and in the next video we'll finally get to the actual pathfinding. So yeah, I'll see you in the next one, and bye.